Hello. Welcome to Gallium Nitride Power Mimics, Fact and Fiction with Chuck Campbell. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by our MTTS Education Committee. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box on the left side of the webcast window, and please don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the slide area. You can also go into full screen mode if you desire. Refresh or reload the current page if you encounter any problems. If you're listening over your computer speakers, you can adjust the media player volume, but remember you may also need to adjust your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides to be presented today. Now let's introduce our speaker. Dr. Charles Campbell received BSE, MSE, and PhD degrees from Iowa State University in 1988, 91, and 93, respectively. From 1993 to 1998, he was with Texas Instruments and involved with microwave module design and MMIC development. Since 1998, he has been with various divisions of Triquint Semiconductor, where he has held positions of Design Team Leader, Design Engineering Director, and Design Engineering Fellow. He is currently an Engineering Senior Fellow with the Infrastructure and Defense Products Division of Corvo. A Fellow of the IEEE, he has served on the editorial board for IEEE Transactions on Microwave Theory and Techniques, as the General Chair for the 2015 Compound Semiconductor Integrated Circuit Symposium, and the IEEE Microwave Prize Selection Committee. He has authored or co-authored over 50 journal and conference papers, and authored an online book chapter on MMIC power amplifier design. Now it's my pleasure to turn the virtual podium over to Chuck Campbell for Gallium Nitride Power Mimics, Fact and Fiction. Chuck?
All right, well, thank you, Mike, for the introduction, and thanks to everyone that's joined in this webinar. As you can see from the title, my talk will be on gallium nitride power integrated circuits. And most new MMIC designs today do use gallium nitride technology. Now, there are a number of good reasons for this. GaN has many attractive characteristics. Its high breakdown voltage allows high operating voltage capability. GaN also has higher Imax than the incumbent gallium arsenide technology that's currently replacing for power devices, about 60% higher, in fact. And you get all this with good microwave performance. GaN devices are really almost as fast as their gallium arsenide counterparts for a given gate length. They have high gain, high FT, and high max, and like most high-speed field effect transistors, they also have good noise performance. Now, probably the best thing about GaN process technology today is that it can be built on high thermal conductivity substrates such as silicon carbide or silicon. Given all these points, it really should be the ideal technology for microwave power applications. In fact, GaN technology's use is rapidly growing. It first showed up in the military systems, radar, electronic warfare, and comms. However, it's now used quite a bit in infrastructure, including base station, SATCOM, uplink, and commercial radar applications. It's finally starting to actually show up in commercial applications as well, specifically cable TV and commercial test equipment. Numerous circuit functions have also been demonstrated in GaN technology. The most common one is, of course, power amplifiers. However, low-noise amplifiers have been designed that have very high input power handling capability, and GaN is also quite useful for high-power RF control components, such as microwave switches, phase shifters, and attenuators. GaN MMIC design, however, is not without issues and problems. Some of these are obvious. There's high voltages and high currents present on these ICs. So things like thin film capacitor breakdown voltage and microstrip trace current handling has to be taken into account in order to ensure reliable operation of these chips. These devices are also power devices, so they get hot, and like anything that's getting hot, thermal issues have to be considered. But some of the problems that were encountered were much less obvious. Wideband power amplifiers in particular were difficult, as well as power combining. And of course, the user interface and driver circuitry. Customers had to get used to using high voltage supplies as well as high current supplies. And for those using control components, they sometimes had to switch between 0 and -30 or -40 volts in a few hundred nanoseconds in order to meet system specifications. Doing this was found to be quite difficult. Okay, so the first thing people talked about when these high voltage processes came out is that these devices should have high output impedance, so you should be able to build wider bandwidth amplifiers. Well, indeed, high voltage operation does equal higher output impedance for most transistor technologies. This should translate into reduced transformation ratios for very high power amplifiers. A reduced transformation ratio should mean a simpler, lower loss, wider band matching network. Or less complex power combining, or if you're using the same level of complexity, you should get much more power using GaN devices instead of Gallium Arsenide ones. All of these points were true in some cases. Narrow to moderate bandwidth designs do benefit from these features, as well as wideband designs at low frequency. In other words, designs with high fractional bandwidth but not wide absolute bandwidth. Where we ran into trouble was reactively matched wideband microwave frequency designs. There were a number of existing Gallium Arsenide power amplifiers that operated in the, say, 6 to 18 gigahertz range or 2 to 12 gigahertz range, and these parts put out a few watts, and it seemed obvious to drop gallium nitride transistor models into these designs, re-optimize them, and one should be able to get 3 to 5 times more output power. And that's exactly what we did. The designers came back after a couple of days and claimed, I can't get good performance out of this design doing this. I don't really understand why. Well, after digging into it a bit further, it turned out that we were running into a fundamental matching restriction that MMIC designers were really not very familiar with, and that is the Bode-Fano limit. So the Bode-Fano integral is shown here on this page on the left for a parallel RC circuit. A parallel RC circuit is the one that's most commonly used to model the source impedance of power transistors. Those circuit elements for that circuit are RP and CP. These parameters are generally known ahead of time. In other words, they can be measured using load pull, or they're on manufacturer data sheets for the transistor processes. Gamma in this integral is the reflection coefficient that you're able to achieve. Now, this is integrated over frequency. It has to be less than pi divided by RP-CP. So what this expression basically states is that for a given quality of match, there's a limited bandwidth over which you can achieve it. Now, the Bode-Fano integral is difficult to evaluate in closed form for real reflection coefficient functions, such as the one shown in blue on the plot on the left. Now, I'm showing this in return loss, which is simply the reflection coefficient given in decibels. However, if you approximate this with the red rectangle, then you can do the integral and come up with a closed form expression for bandwidth, which is the second equation on the left side. As you can see by looking at this, if the RP-CP product is large, you get lower Bode-Fano limited bandwidth. Also, if the quality of match is very high, or you get a very large return loss, you also get lower bandwidth. Now, RP is approximately a linear function of the power supply voltage, or shown as VD in the final equation on the left-hand side. VK is the knee voltage of the transistor IV characteristic, and Imax is the transistor's maximum current capability. Beta is a fitting factor, which is generally between 0.5 and 1, depending on what type of a match you're trying to achieve and the transistor technology. Okay, here's what RP and CP look like for a real GaN device. These curves were collected from load pull data on a quarter micron GaN FET and from load pull measured over a range of drain voltages. Okay, RP is shown in blue. And as you can see, as that equation predicted on the prior page, it's a pretty linear function of a supply voltage. If you double, the drain voltage, you more or less double RP. The capacitance, CP, is a somewhat weaker function of drain voltage. It does decrease as the drain voltage is increased due to decreased depletion capacitances, but it doesn't decrease nearly as much. So the RP-CP product does increase with power supply voltage. It increases rapidly at the lower voltages, and it starts to saturate when you get to the maximum voltage capability of the transistor. So higher supply voltage, which people use to get more power out of these GaN devices, definitely does lower the Bode-Fano limited bandwidth. Okay, so why does this really matter? People designed gallium arsenide MMICs for decades and never had to even think about Bode-Fano limits. Well, for a 6-volt gas gallium arsenide power PHEMT process, if you enter RP and CP into that equation, you get a Bode-Fano limited bandwidth greater than 30 gigahertz. Well, 30 gigahertz is extremely wide band, much wider than one would generally attempt to match with the reactive matching network. So the reason that we never ran into this problem with gallium arsenide is that we just never tried to do enough bandwidth where we would see the restriction. The same is not true for GaN. So if I take that plot I just showed you at 35 volts, I get RP of 120 ohm millimeters, CP of 0.3 picofarads per millimeter. This works out to a Bode-Fano limited bandwidth of less than 6 gigahertz for a 20 decibel quality of match. And 20 dB really isn't all that good of a match for most power amplifiers. So no wonder those original designers were having a hard time designing a 6 to 18 gigahertz or a 2 to 12 gigahertz power amplifier. They were running into the Bode-Fano limit, which cannot be violated. Of course, this is a theoretical calculation. It assumes an infinite order lossless matching network, which of course is not practical on an actual integrated circuit. So in practice, the Bode-Fano limit for a 35 volt GaN device might be more like 3 gigahertz. So you've really got no chance of designing the wide bandwidth amplifiers that people originally set out to accomplish. All right, well, talking about, theoretical Bode-Fano limits is fine and well, but this type of thing is not going to stop customers, program managers, or marketing managers for asking for wideband amplifiers. So one needs a way around this. Now, if the capacitance is reduced, I get more bandwidth. Well, absorbing device capacitance into external structures is a well-known technique, and it's the fundamental idea behind the distributed amplifier, which is used considerably in gallium arsenide technology, particularly in the fiber optic area for modulator drivers and circuits of that type. Shown here is the basic circuit topology for a uniform distributed amplifier. By uniform, I mean the artificial transmission line impedances, ZD and ZG, are all the same as you move along the amplifier. Now, the way this works is that the output capacitance and the input capacitance of these transistors are absorbed into an artificial transmission line structure. So the transmission lines ZD and ZG are going to have high characteristic impedances. They're going to look inductive, and that forms an LC ladder circuit. Now, an LC ladder circuit can be used to approximate transmission lines over a certain amount of bandwidth. And the amount of bandwidth where the approximation is a good one depends on how much capacitance you're trying to absorb into the line. And this bandwidth is generally referred to as the cutoff frequency for the amplifier. Now, the output capacitance of most devices is quite a bit less than the input capacitance. So in most distributed amplifiers, the input artificial transmission line would set the cutoff frequency, which would set the bandwidth for the amplifier. So this can be mitigated to some extent by adding those series capacitors CG. Those capacitors add in series with CGS of the transistors, two capacitors add in series to form a smaller one, so you end up with less capacitance at the node where it connects to the gate artificial line. By designing these CGs properly, the gate and drain lines can have the same cutoff frequency, and thus that sets the frequency for the amplifier. Okay, so let's replace these with GaN devices. We should get a higher power distributed amplifier. Well, the reason that doesn't work all that well is the uniform distributed amplifier makes a very bad power amplifier. As I mentioned earlier, to get optimum power performance, you have to match to the source impedance of these devices, which is RP and CP. CP is then absorbed into the line, leaving you just matching to RP. Well, this structure does not match these transistors with RP along the entire structure. Each device will see a different load impedance, and it'll also vary over frequency. Also, some of the power that comes out of these devices travels to the left and ends up dissipated in that termination resistor, R sub LD. And the third reason is that the RF input swing is largest at the input of the amplifier, labeled RFN, and it gets smaller as you move along the circuit. So each of these devices is non-uniformly driven as well. So those three facts conspire to make this a very poor power amplifier. So to mitigate that issue, the non-uniform distributed power amplifier topology was developed back in the 70s. Okay, it's shown here, and it's got a couple of key differences. The first one is that output termination R sub LD has been removed. The output impedance of transistor Q1 serves as the termination for the output transmission line structure. The second difference is the output transmission line impedances, labeled here as Z0, N, are varied as you move along the structure. If this is done properly, at least in theory, you can load each transistor with RP at the same time and independent of frequency. The final difference is those capacitors that voltage divide, or that capacitor divide the input of the amplifier and increase its bandwidth, are varied along the structure as well, with the small ones occurring near the input, and they get larger as you move along the structure. If this is done properly, you can equalize the RF drive for each of these transistors. Now the drain transmission line, Z0 sub N, that first one connected to Q1 tends to be the highest impedance line, and it reduces as you move along the structure, with the last transmission line being equal to the, having a characteristic impedance equal to the load R sub L. Okay, so how do we figure out how to vary these straight line impedances? Well, it turns out there's a fairly simple equation that can be derived to approximate this. Okay, shown here is a very simplified model for the nth transistor. It's simply a current source, IQ sub N. To the right of that current source, we should see impedance Z naught sub N. And looking into that structure, we should see Z naught sub N minus 1. Of course, that node will be driven on the left side by the currents from all the transistors to the left. That's that summation of I sub Q sub I. The negative sign is related to the fact that those current sources are directed out of the node. Okay, applying Kirchhoff's current law at that node, we can derive the following simple expression, which can be rearranged to what's seen on the right. That voltage V is the voltage that simply forms due to all those currents driving that load Z naught sub N. Okay, so what we want to do is design those Z naughts such that every current source sees the optimum impedance, R sub P, looking up into that node. So for the nth device, that's R sub P sub N. Well, that driving point impedance will simply be V over negative IQ sub N. Again, the negative sign is due to the orientation of the current source. So we can solve that equation for R sub P sub N and get the expression that's shown. Okay, note that there's a ratio of currents in the middle expression. Well, if all these transistors are of the same technology, which of course they are because it's an IC, they're all loaded the same and they're all driven the same, it stands to reason I can replace that current ratio with a ratio of the actual device sizes, which is the WQ sub I. So So I'm replacing the current ratio with transistor peripheries. And I rearranged the index of summation as well. Well, this equation can be normalized by multiplying RP sub n by the size of the nth device and solve for the transmission line impedances to produce a pretty simple expression for the Z0 in a non-uniform distributed amplifier. RP, of course, is just the device, is set by the device technology and the power supply, and again, available through measurement or from the manufacturer. Okay, now we know one of those drainline impedances. That last one, Z0 sub n, is equal to the load. So we can substitute capital N into that expression and rearrange it to what's seen on the right. Okay, this points out sort of an important restriction of distributed power amplifiers. RP is known and is fixed by the power supply voltage, and the load is generally given to you by the customer. What this basically says is that that's a fixed number. So my total transistor periphery is also fixed. Well, fixing the transistor periphery is the same as fixing the output power from the amplifier. Well, this of course isn't good. It's difficult to design these things to produce a arbitrary amount of output power. The only way to increase the output power is to increase the periphery. We either have to turn up the power supply voltage to increase RP. Of course, there's practical reasons why this cannot be done indefinitely. You run into breakdown issues with the transistor, and also it will be hotter, and you may have thermal restrictions. Or decrease the load impedance of the amplifier. All right, so we have an equation. Let's do an example. So assume a 50 ohm load, which is common for microwave systems, 10 transistor cells, and an RP of 120 ohm millimeters, which was that quarter micron GaN FET running at 35 volts. Okay, so 120 divided by 50 says we can use 2.4 millimeters of total periphery in this amplifier. So assuming 3 to 5 watts per millimeter output power from this technology, I'm going to end up with a 7 to 12 watt amplifier. Here's what the drainline impedances will look like if you calculate them out using that equation that was just shown. Now I'm assuming that all the transistor cells are the same size. There's 10 of them, so it'll be 240 microns. You can immediately see an issue. That first transmission line impedance needs to be 500 ohms. Well, 500 ohms is extremely large. The impedance of air or free space is 377 ohms. 2 bond wires above a ground plane, you might be able to get to 200 ohms. I don't know of any way on MMIC technology to get to a 500 ohm transmission line. So they're very high, and they're generally unrealizable. In fact, on 100 micron thick silicon carbide, about the highest transmission line that you can build is about 110 ohms. And this line will be extremely narrow and have a very, very low current carrying capability. Now, it turns out that this can be alleviated to some extent by making the first transistor larger, since Q1 sets the maximum Z0 in that drain transmission line. So if I make Q1 600 microns and the rest of them 200 microns, I'm still summing to 2.4 millimeters, so I'm okay. There's no reason why the devices can't be different sizes. I get the red triangles. Well, this is a little bit better. Now, my first line still needs to be 200 ohms, which is much, much higher than I can do. And the second line can't be realized either. So for both cases, the first couple of transistors will be very poorly loaded. They'll be hot. They'll produce very little power, and they probably will be unreliable. Okay, so let's revisit reducing the load impedance. As was mentioned, this increases output power. At 3 watts per millimeter out, I'll get 7 watts of 50 ohms, but I can double that if I reduce to 25 ohms and go up by a factor of 4 if I reduce to 12.5 ohms. Well, if I start changing load impedances, I'm going to need transformers because I'm still going to end up having to have 50 ohms at the output of the chip. This will reduce bandwidth and potentially add a little bit of loss. But it greatly improves the realizability of the amplifier. Shown here are the drainline impedances required for different load impedances. Note for a 12.5 ohm load, which is the black circles, I can actually realize all of the transmission lines in this particular example. Even at a 25 ohm load, which is the red triangles, I can realize 9 out of 10 of them. This is for uniform cell size, so if I make the first device a little bit larger, I can realize all the lines for 25 ohms as well. Okay, so if I'm going to start reducing load impedances, I'm going to need transformer circuits that are monolithically compatible with GaN technology. It turns out there are a couple of them out there. A particularly useful connection is the Rothroff connected coupled coils, which is shown on this slide. This connection of coupled coils will give you a 4-to-1 impedance transformation. Now, of course, you can't build perfect coupled inductors on IC technology, but we have found that we can get about 4-to-1 bandwidth using Rothroff connected coupled lines on 100 micron thick silicon carbide. So shown here is an implementation of a 4-to-1 bandwidth Rothroff transformer. It works from 2.5 to 10 gigahertz on a 100 micron thick MMIC technology. Note that it has to hairpin back on itself, and that's to accomplish that cross connection that you see in the actual circuit. Now notice that there's a ground on one of those coils. Well, that turns out to be very convenient, because that ground can be replaced by a bypass capacitor, producing an RF short over the operational bandwidth of the transformer, but it allows me to pass DC current over it and inject current into the amplifier. So the transformer not only serves to do the transformation, but can also serve as a wideband bias choke, which is also a bandwidth limiting component on these circuits. Of course, this is a highly distributed structure, so you better use EM simulators to actually do the design. Okay, what if I need more bandwidth? 2 to 18 gigahertz is another very popular band used in many systems. Well, it turns out I can use a lower transformation ratio and actually get more bandwidth. A transformer connection that accomplishes this is the trifilar transformer, which is shown here. This transformer can produce anywhere from 2.25 to 1 to 1-to-1 transformation, depending on where you tap the output of the transformer structure. Again, we can't build perfect coupled coils on silicon carbide. However, designs on GaN processes have shown that we can accomplish 10-to-1 bandwidth with trifilar connected coupled lines. Here's an example shown here. This transformer operates 2 to 20 gigahertz, and the output, the 25 ohm port, is tapped at a point that gives us 2-to-1 transformation. And like the Rothroff connection, the trifilar connection does have one of the coils shorted, which provides an integrated bias injection point for the transformer. Okay, a couple of MMIC examples. Here's an 18 to 40 gigahertz chip that uses a Rothroff transformer, and you can see it's circled in red. The high frequency makes it very short, so there's not a lot of length to it. And 2 lines are used instead of 4, as was seen in the prior example. The output stage for this amplifier is on the right. For 12.5 ohm load, we can use uniform transistor cell sizes. You can see most of those sets are the same size. This is a 3-stage amplifier. The other 2 stages exist on the right-hand side of the chip. Okay, here's some measured performance for that particular amplifier. It produced about 25 dB of linear gain and a good input and output match over the 18 to 40 gigahertz operational bandwidth. In fact, this chip actually works down to 16 gigahertz. The plot below, the S parameter gain plot, shows output power. And as you can see, under saturated conditions, this die produced between 6 and 9 watts of output power over most of the 18 to 40 gigahertz band. The power did drop down to about 4 watts right at 40 gigahertz. Try buying a 7 or 8 watt 18 to 40 gigahertz amplifier by just pulling up catalog parts. You'll have a difficult time doing that. So GaN really, is a big game changer for this type of output power level and bandwidth. Here's another example. This one uses a trifilar transformer, and it operates over a wider band. This design works 1 to 8 gigahertz, that's 8 to 1 bandwidth. The trifilar transformer is circled in red. It's a two-stage chip. A trifilar transformer produces a 25 ohm load, so as you can see, that first set down at the very bottom has to be made larger than the other ones to realize the output transmission lines on the drain side of that output stage. Again, this is a two-stage device. Here is the performance measured from it. Produces about 30 dB of gain over the operational band. The output power saturates out at about 10 watts, and peak power efficiency is typically greater than 30% over the 1 to 8 gigahertz bandwidth. Okay, so these are power devices. Most GaN devices are built on silicon carbide, which has really high thermal conductivity. So I should be able to get the heat to the back of the die pretty effectively, and thermal analysis shows you actually can. Where you run into trouble, however, is that these GaN chips are really about the same size as the Gallium Arsenide power amplifiers they're replacing, but they produce 3 to 5 times more output power, and they have similar power added efficiency. So you get 3 to 4 times more heat flux that has to be removed from roughly the same area. The early adopters of these amplifiers were not really prepared for this, and they were unable to remove this amount of heat. The inability to move heat produces higher base temperatures in the MMIC specifications. So today's designers still must practice good thermal management when designing these chips. One way to do it, design them for efficiency, or power PAE. If you don't make the heat, you don't have to get rid of it. You can separate the gate fingers in the actual transistor cell. The heat is generated underneath them, so pulling them further apart means they heat each other up less. Of course, you cannot do this indefinitely because then the transistor gets so large that the microwave performance falls apart. If you're combining many cells, you can try to separate them. This will, of course, increase the die size, and in some cases make it more difficult to stabilize the part to eliminate unwanted oscillations. A cell that's often used is the ISV cell, or individual source vias. You see these vias, which are the rectangles that are going downward, provide a ground point connection to the sources of this transistor cell. In an ISV cell, you're effectively combining a bunch of two-finger cells, so you can separate the gates and still maintain really good microwave performance. Here's just an example of thermal management. The staggered transistor cells that you see at the top of this chip are not for electrical reasons. The designer did this simply to get them further apart so that they heat each other up less. Okay, here's an interesting example. This is actually a 20 millimeter GaN discrete transistor cell. That's that chip in the middle. And the customer using this built a couple of load pull pre-matches so they could collect the load pull data on this cell in order to design a larger amplifier. Well, they complained back to us that they kept getting 1 dB lower output power than they expected, and they saw a very odd thermal scan. The white areas are the hottest, and this part was hottest along the edges and coolest in the middle, which is exactly the opposite of one would expect to see. So upon further investigation, the more detailed analysis of this circuit, by using a EM simulation for the pre-match and hooking up 16 individual nonlinear models, we can monitor the output power from each cell. The output power was shown as the blue triangles. We should be seeing about 4.5 watts per millimeter, which we do see for a couple of the cells. But the ones near the top and the bottom, or cells 1 and 2 and cells 15 and 16, produce a very low amount of output power. These cells are poorly loaded, and they will be getting very hot. So that explains the thermal scan that was seen. Also, if you integrate these powers over the length of the device and normalize it to the 4.5 watts per millimeter we should be expecting, you get about 9/10 of a decibel reduction in output power. And this agrees pretty well with the 1 dB reduction the customer was reporting. Okay, so power amplifiers are one of the most published subjects you see in IEEE microwave area. But almost all those publications use one transistor cell. They rarely ever combine more than one of them. And they use exotic, switch modes of operation to get high efficiency. When you do see publications that combine cells, generally only results are seen. There's very little detail on how the actual combining was achieved. And there's a good reason for that. The combining is where the difficulty occurs. That's where the intellectual property is in these designs, and generally companies don't want to share much about it. Now the example that I just showed you on that discrete 20 millimeter cell, the issue with that was caused by asymmetries in the combining network, or the pre-match. Causes of asymmetries are many. Mutual inductance of parallel bond wires is one issue, and that's probably what was occurring in that prior example. You can also get mode formation due to curves and bends. Coupling between parallel microstrip lines. Microstrip lines driven in the even mode will not have the same impedances if a couple of them are in parallel. Sharing source vias between adjacent transistor cells changes the effective inductance of those vias, again when driven in the even mode. And of course, transistor cells can heat each other up, which changes their performance and causes asymmetries. Here's an example of a chip that's got a lot of issues with asymmetry. This is actually a Gallium Arsenide device, 3 stages, 16-way combining on the output. You can see there's lots of curves and bends, lots of parallel microstrip runs of line, and that 16 transistor cell stack in the output shares the source vias. Well, this part had issues with low output power, and again it was tracked down to asymmetries in the matching networks. Shown here is the output powers from the first, second, and third stage transistors. The black ones are the first stage. Both devices look similar. You can hardly see any difference between the two traces. You see a little bit of difference in output power in the second stage. By the time you get to the third stage, that output power is significantly different. Instead of the 1.1 watts per millimeter we were expecting, some of the devices are only putting out 800 watts per millimeter, and that explained the reduction in output power. Okay, shown here is a simple example of how these asymmetries can creep into a design. So this is a very simple binary combiner. The transistors are represented by a couple of nonlinear models for 0.15 micron GaN transistors. So the procedure of designing here would be to EM simulate the combiners. In the simulator, optimize the source and load gammas, or their impedances, using ideal tuners to maximize the output power from the circuit. Now, if you do this, you get 31.7 dBm. That's 3.8 watts per millimeter for each of the transistor cells, which is what would be expected from this process. Also, the loads that show up on each of these cells are the same, which again you'd expect from a simple symmetric combining network. Okay, so let's add a curve to the output network. I might do this to hook these two cells up to two other cells to make a 4-way combined amplifier. So going through the same procedure, re-AM simulate this, re-optimize the gammas. Now I get 31.6 dBm out. That's a tenth of a dB less. That's probably due to maybe loss in that curve. That's what most people would assume. But I get a little bit less output power from each transistor. Now that I would not expect if it was due to loss in that curve. Also, the loading on the two devices now is slightly different, but it's still pretty close together. But I'm seeing a little bit of asymmetry. Now, a tenth of a dB, not a big deal. I'll probably just continue on. Okay, if I put a curve on the output, I'm going to have to put one on the input in order to connect these two devices up to two other ones to make a 4-way combined amplifier. So MMIC designer will go through the same procedure. Re-EM simulate this, re-optimize the load impedances. But now the best I can get out of this is 30.2 dBm. That's 1.7 decibels less than that simple structure with the straight lines. So in other words, changing the input completely destroyed the performance of this very simple circuit. The output power density of each device is well down too. It's down to 2.8 watts per millimeter. These devices are no longer operating efficiently. They're going to be very hot and they're going to be unreliable. And the loading is very asymmetric. Okay, what in the world happened? Well, that output curve just caused a minor problem. And that difference was due to current imbalance due to more mode formation around the curve. When the current goes around that curve, it's no longer going to look the same as when it's straight. And if that mode formation doesn't settle out before you hit the transistors, they no longer get driven with the same amount of current. However, the input one caused a really large issue. Well, the same thing happened. However, that small amount of current imbalance got amplified by the transistors to make a large amount of current imbalance at the output. This current imbalance actively load pull those two transistors well away from their optimum loads. So in other words, an asymmetry on the input of a power amplifier stage completely destroyed the performance of the amplifier. Normally when you design power amplifiers, you don't worry about the input so much, you just worry about the output. Well, when you're power combining, you do have to worry about the input. Now, if you're watching for this, if you design the part, it's pretty easy to fix. Odd mode suppression resistors, which you have to add anyway to get rid of parametric and odd mode oscillations, will help. You can shift the T-junction as well. In fact, anything you can figure out to get rid of the asymmetry is okay and will work. You don't have to do what I'm showing you. There's a compensated design. I've added odd mode suppression resistors. I've shifted the T-junctions upward. If I analyze this, I'm back to 31.7 dBm. So adding those curves really had an insignificant amount of loss, and I'm getting the full power out that I'm getting when they were straight. And my loading is now symmetric, and it's back to where it was to begin with. Okay, so I've been talking about combining individual transistors so far. In many amplifiers, though, entire amplifiers are combined. The most common approach is the balanced amplifier. This is done with a 90-degree hybrid. The 90-degree hybrid has a nice property that if I connect two identical amplifiers with imperfect matches up to the output ports, which are shown on the right, those reflections will combine at that termination resistor, which is shown in light blue, and be dissipated. They cancel at the input port, which is shown at the top on the left, and the reflections cancel out, and I get, in theory, a perfect match at that point. The most common 90-degree hybrid is the Lang coupler, which is shown here. Lang couplers work really, really well on MMIC technology. This V-band example, two of them measured back-to-back, has only got about 0.2 of a dB of loss at 60 gigahertz, which is really quite remarkable. Here's an example of a balanced amplifier. This is a Ka band device. You can see from the frequency range, it's for VSAT uplink applications. Well, two 6-watt amps are balanced together to produce a 10-watt amp or 40 dBm output power amplifier, shown by the blue curve. The power added efficiency of this part is also quite good, shown by the red curve. It's between 20 and 25%. Now, I mentioned reflected powers are dissipated in the termination resistor. So you have to be careful with power amplifiers that that's made large enough to handle the worst case load that a customer might put on the device. A factor of 4 is a good rule of thumb for balanced amplifiers. If you expect 10 watts out, your termination resistor should be able to handle at least 2.5 watts, and generally it will not be destroyed for the worst case load that's connected to the part. Here's sort of a final example. This combining of amplifiers uses a traveling wave combiner. It actually combines 5 unit amplifiers. As you can see, they're vertically and are 3 stages. It uses couplers as well. Each of these couplers has a different coupling coefficient that couples off just the amount of power needed, such that each of the 5 unit amplifiers are driven with exactly the same input power. The same coupler is used in reverse at the output to gather up the amplified powers in the correct ratio, such that they add coherently at the output of the chip. As you can see from the plot on the right, this approach works extremely well. This amplifier produced 2 to 2.5 watts of saturated output power from 75 to 100 gigahertz. Again, this is a device that you would have a very, very difficult time buying an off-the-shelf amplifier with this level of performance. Okay, so in conclusion, GaN MMIC technology is a real game changer. And I really consider myself fortunate for this particular technology to show up during my career. Not very often does one get to see a step function improvement in performance in a technology in a normal span of one's engineering career. The enabling characteristics still, however, come with some issues. I've tried to share some of the ones I found were more interesting with you today and how they were fixed. All right, well, thank you very much for your attention. That concludes my talk.
Great, thanks a lot, Chuck. That was very, very informative. Lots of great information. I will also mention to the audience that in the slides that you can download, there are additional slides that we weren't able to get to today, and so you can check those out. Okay, so now it's time for our question and answer session. And before we start, please remember that you can still submit questions through the Q&A panel. So please do that if you have questions. And so now we'll go on to our first question here. So how do you estimate the power handling of the transformers that you're using in these chips?
Okay, so the first thing that has to be done there is if you are using them to bias through, you have to make sure you're not violating the electromigration or current density rules to the process. And then, of course, you can do a thermal analysis on the transformer by just looking at the EM simulated. So when you do the EM simulation, it'll predict current densities from which you can estimate power dissipations. And of course, the final step would be to actually do a thermal scan of the transformer once you've built the part. So those are sort of the approaches that I would probably do to try to ascertain whether or not I had enough power handling in that transformer.
Okay. Do you have any comments on the biggest challenges of using GaN at millimeter waves? For example, are shorter gate length processes needed?
Yeah, and there are shorter gate length processes. In fact, some companies like HRL and Raytheon have demonstrated, very, very high performing amplifiers up at W band and even a little bit higher than that. And so the short gate lengths do exist. At Corvo, the shortest gate length on a production release process is 0.15 microns. But we are working on shorter ones as well. But really, the millimeter wave designs are similar to the Gallium Arsenide ones. It's just that everything has got to be able to handle higher levels of current and voltage for the components that exist on the MMIC.
Okay. So in these processes, typically, how many metal layers are there?
That'll depend on the foundry. Corvo has a 3 metal layer process. I'm not really certain how many metal layers other foundries have, but you generally got to have at least 2. You've got to have some sort of a seed layer that could be used to plate off of, and so that's very smooth to be used for thin film capacitors. And of course, a thicker plated layer to handle current, and that'll generally also be used for air bridge structures.
Okay. Let's see here. How did you monitor the power from the individual devices for these power combining schemes to look for the imbalances?
There's generally a power meter element that most of the circuit simulators have available. If the simulator you're using doesn't have one, then you can actually put a current meter and a voltage meter and just calculate it in the equation block. So either approach will work.
What about for the hardware?
Well, of course, we don't monitor the power for hardware. Those are all simulations that I showed output power
okay,
right. Itself.
Okay, all right. Let's see here. There's a question about the return loss on slide 18. Can we go to slide 18?
Slide 18 didn't have any. How do I, okay, push to the audience, all right.
Let's see, yes, I just...
Okay, so I didn't see any return loss on that slide.
Yeah.
It's just load impedances.
Oh, those are, so RL is the load impedance. Okay, that must have been just a confusion.
Yeah. Yeah, so you have 50 ohms on the output port of the transformer, and that's the impedance you would see on the input port. We're actually able to design transformers that have very good return loss still looking into that input port, typically in the 20 dB range.
Okay. Yeah, so for the audience member that asked that question, if we answered that, let us know. If not, the RL is for load resistor, not return.
Yeah, so that's the impedance. Yeah, that's the impedance you'll see looking into the transformer when you 50 ohm load the other side of it.
Okay.
And transformer losses are in the half a dB kind of range over their operational band, so they're high performing components.
Okay. Here's a good one, I think. Maybe. What packaging problems, if any, did you find with millimeter wave GaN?
Okay, I am not a tremendously knowledgeable in the packaging area. I do know that we do package these high frequency parts, and thermal is always the biggest issue. You just have another layer of a material you got to pull the heat out of. The millimeter wave packages really just look like a big thick copper moly or some other high conductivity metal carrier with microstrip lines running right up to it, so they're not tremendously different than just testing the MMIC, as a die. But thermal issues are going to be the largest problem with packaging generally.
Okay. In your fixture for testing the power amplifiers, how did you, or could you provide any comments on how you did perform the de-embedding to get to remove the loss of the fixture?
Okay, well, of course, whatever fixture is used, a set of Cal standards is also built to match the de-embedding lines that are used in the fixture, along with the same connectors. Many of these higher frequency parts are tested with probes, in which there's an alumina de-embedding line, and then, of course, the bond wires are hooked to the MMIC, and we have Cal standards that, again, are the same as that alumina de-embedding line, so you can do a TRL calibration right up to the interface where the bond wire connects.
So standard de-embedding procedure.
Yeah. Yeah, you just got to make sure you build your Cal standards, early on when you've turned the design in when you're building your fixture.
Right. Okay, it looks like we got a little clarification on the return loss. He says, sorry, slide number 35. So.
Okay, let's go to that one.
Yep, I'll advance us to where it shows.
Okay, so that's not really return loss.
Yep.
That is that's the load that each transistor cell is presented by this network, where those gammas have been optimized in the simulator to get the most output power possible out at, I believe, 30 gigahertz.
Okay, so it's essentially just showing the impedance that
the load impedance.
Yeah, the load impedance. Okay, so not return loss.
That
okay.
Should be a conjugate match to RPCP.
Okay. Let's see. Okay, with such big power combining structures, what is the largest MMIC size that's available and that's reliable?
Ironically, our MMIC sizes are set by how big of how much area the E-beam machine can expose. And so
okay,
right now our maximum size is about 10 by 10 millimeters. We have an example of an L-band power amplifier that puts out, hundreds of watts that's probably 7 by 7 millimeters square. So we're able to cut that out and put it in a waffle pack without cracking it.
Okay, so it's not necessarily related to. It's not necessarily related to substrate size either. It's more of how much area you can pattern.
Yes.
Okay.
Yeah, different EV machines can focus over different ranges.
Right. Okay, I guess here's a forward-looking question. I don't know if. Well, I'll just ask you. So what's after GaN? Diamonds?
Yes, I think so. And it's a ways out there because trying to dope diamond is extremely difficult. But it won't surprise me if us being carbon-based life forms end up with carbon-based technology. Diamond for electronics and carbon fiber for everything mechanical.
Agreed. Would be good for thermal as well.
Yeah, tremendously.
Yeah. Okay, so this was a follow-up question. Maybe this will be our last question. It's a follow-up to the fixture and de-embedding question. So they're asking, or they're stating that they were under the assumption that for high-power testing, you assemble the MMIC into a fixture. And have you had good success, or so alternatively, have you had good success testing for large signal performance on wafer?
Yeah, but we pulse it. We'll pulse the drain bias on wafer. And you almost have to do this because after about 5 watts of power up at Ka band, you'll actually melt the solder in the probes if you go continuous wave. We RF test every wafer as part of the manufacturing line.
Right.
And so yeah, pulsing is how we can perform.
Yeah. Okay. I think that's we do still have some questions left here in the queue. So we'll get the presenter to follow up on those questions offline. Also, let me go ahead and do this. So as we said earlier, this session will be archived on the Society website at mtt.org, and all the registrants will get an email reminder with that website address when it's available. For the attendees who would like to receive PDH credits, please follow the link in the webcast view and use the code that's provided on the last slide of this presentation, or the slide that's shown right now in the live view. Once again, I'd like to thank Dr. Campbell for this excellent and very informative presentation. And our special thanks go out to our audience for joining us today. We hope you found today's event valuable and that you will return for future IEEE Microwave Theory and Technique Society webcasts. So thank you and have a good day.
All right, thank you, Mike.